So today we will continue talking about decomposition methods. We will cover what is called Augmented Lagrangian and ADMM. ADMM is the acronym for Alternating Direction Methods of Multiplier. The reason we want to spend one lecture on this is because ADMM is a quite active research area, but it is not as mature as some of the other decomposition algorithms we've covered before. So you can view Augmented Lagrangian and ADMM as an extension of Lagrangian decomposition we covered in the previous lecture. The only difference is that in this lecture, we will not focus on mixed integer linear programming problem. In the previous lecture, when we discussed Lagrangian decomposition, we use MLP as the motivating problem because MLP also have some nice properties like Mayer's theorems, this characterization using extreme points and so forth. The thing is, Augmented Lagrangian and ADMM for MLPs are not as mature. It is still an active area of research. If you check the papers, most of the papers are published in the next 5 to 10 years. So it is still an active area of research. That's why we will not focus on MLPs in this lecture because it's still a very hard problem to deal with if you want to study ADMM. You can read the latest papers. As I said, most of the papers are published in the next in the last 5 to 10 years. We will instead focus on continuous and convex problem in this class, right? Because continuous convex problems are relatively well studied. There are very strong properties related to continuous convex problem if you apply these two methods. Okay, so before we introduce what is Augmented Lagrangian, let's do a very quick review of what people call dual ascent. So essentially, dual ascent is a subgradient method we discussed in the previous lecture. But as I said, in this lecture, we will focus on convex problem. Right? So you'll see that very quickly, what is a dual ascent, right? So remember in the previous lecture, we talked about subgradient method, which is essentially, you can prove AX minus B when X is the optimal solution of the Lagrangian subproblem, give you the subgradient of the dual problem, right? And then you can do something like a subgradient descent or supergradient ascent. So what dual ascent is essentially the same thing, but initially, of course, it is applied to convex continuous problems rather than MLPs, right? And of course, the theory we discussed in the previous lecture still holds since, the theory we discussed in the previous lecture are proposed in general for general optimization problem. Here, if you deal with a specific simplified class like linearly constrained convex problem, it will still hold. Okay, so that's just a few contexts on how it is related to the previous class. Now, if you don't remember what we talked on Tuesday, let's just discuss this from scratch, right? So here you have a function minimize f of x subject to a linear equation constraint. Well, you can write down the Lagrangian of this problem. It's very simple, right? You just dualize this linear equality constraint, and the Lagrangian is f of x. Let's assume y is the dual variable here, y transpose ax minus b. Right? And you can define the dual function as minimize x over this Lagrangian L x of y. Right? And the dual problem is to maximize the y, right? Trying to get a dual multiplier that gives you the tightest bound. Yeah.
Is f of x required to be linear in this case, or would it work nonlinear?
Yeah, so let's assume f of x is can be nonlinear convex. Yeah, okay. Yeah. Now, how does the dual ascent algorithm work, right? So let's assume at a given iteration, you first fix the yk variable to the dual you got from the previous iteration, right? So if you don't know how to get the yk in the first iteration, just choose yk equals to 0, right? Yk equal to 0 is like you are not even penalizing the violation of the equality, right? So now you solve an unconstrained problem to get x in the first iteration. But of course, as you keep updating the y, you can fix y as the y you got in the previous iteration. So with a fixed y equals to yk, you can optimize x, right? So this is like an unconstrained convex problem, right? If you fix y equals to yk, this L is f of x plus yk transpose ax minus b, right? So I said f of x is a convex function, and yk is a constant. You fix using the yk from the previous iteration. A is a constant, so it's a convex function plus a linear function, right? So therefore you can get a minimum at this iteration. Now, the important thing is after you update the x, how do you update the y, right? The way you could update y is to take a gradient step with respect to y, right? So in the previous lecture, if you recall, we already proved that ax k plus 1 minus b is a subgradient of this function gy, right? So we proved that if you want to dualize the complicating constraint, right, and you solve the Lagrangian subproblem, then this complicating constraint evaluated at the optimal solution of the Lagrangian subproblem give you a subgradient. Okay, so if you take this direction, it will increase the objective. It is a supergradient, not a subgradient, since you are maximizing. So this gives you a ascent direction for y, right? You can keep going using this supergradient direction. Yeah.
Isn't this kind of the same methodology that we use for outer approximation?
The outer approximation. Well, that's an interesting perspective. Yeah. So outer approximation is like you are linearizing a convex function, right? So you can think about this gradient is if you take this gradient, it gives you an outer approximation of the function g of y, right? So outer approximation is more similar to the cutting plane methods per se, right? So you keep adding those outer approximation cut because you know this gives you a super gradient, right? You can keep outer approximating the function gy. And then this gradient ascent is more like gradient descent we covered in unconstrained optimization problem. You first show that this thing is a super gradient for MILP problem. For convex smooth problem, it might be a gradient. Right? So you can use this gradient direction to keep improving your objective function g of y. Okay, yeah. Okay, so the notation might make you a bit confused because we are slightly using different notation. But if you remember, in the previous lecture, ax less than equal to b is a complicating constraint, right? Here we just write equality constraint, ax equals to b, right? So basically the complicating constraint evaluated at xk plus 1 give you a super gradient direction. Okay, and then you can choose the step size alpha, right? Again, from the last lecture, we went through very quickly. Choosing the alpha is not a trivial choice. You can use different heuristic of choosing alpha. Okay, yeah, so this is a dual ascent, just like the subgradient method we covered before, right? And then let's discuss what is called Lagrangian decomposition. Again, it is like a review of Lagrangian decomposition. But instead of applying to MILP problem, we apply it to some convex problem, right? And some people call it dual decomposition because you dualize some complicating constraint. Okay, so here let's assume the objective function f is separable, right? So let's assume x can be decomposed into capital N subblocks of x variables. Then the objective function can also be decomposed by x1 all the way to x capital N. Okay, but let's assume you have some sort of complicating constraint represented by AX, right? Let's assume we have separated the columns of A and write AX as a summation of AIXI, I from 1 to n. Right? So AX equals to B is your complicating constraint. Now, this is the same thing as Lagrangian decomposition we covered before, right? You could dualize this complicating constraint by multiplying the y variable, the dual variable here, and you get this form of problem, right? So this means if you want to minimize x, right, you can split it into different blocks, right? Just like what we did before. Each xi can be a scenario in stochastic program, or it can be a machine in this assignment problem we talked about before, right? Instead, here we introduce a notation using convex nonlinear problem, f of x instead of C transpose xi. Okay, yeah. So with that, you can optimize all the xi's in parallel. After you got the optimal x, you can still perform this gradient ascent step or dual ascent step to update the dual variable. Okay, and then in the literature, you will find out some people call it this method dual decomposition instead of Lagrangian decomposition, right? But it's actually the same thing. Each iteration follow the following operation, right? You need to send the dual variable to each of the subproblems, and then you update all the xi's in parallel, right? So you can think about if you have a parallel machine, each of your CPU can be responsible for solving one of these xi subproblem, right? And you can have a process that gather all the xi's you got from each of the subprocess, and then together, after you gathered all the xi's, you can update the dual variable. Okay, and this is a very old concept back in the early 1960s, especially for continuous convex problem. But for mixed integer linear problem, it is it was developed a little bit later than that. Okay. Yeah, so the thing with this problem is it can be quite slow, right, to converge for these type of problems. So what are the issues with dual decomposition, or the limitations of dual decomposition? Right? So we will first introduce its limitations, and then we will show you how augmented Lagrangian or ADMM can handle these type of limitations. The first limitation is computationally, the convergence can be quite slow. Yeah, if I just say that, you may not believe that, but maybe you could try a toy problem and implement that to see how it works. Right? Typically, it involves quite some tuning over this step size alpha. Right? So in the previous lecture, we introduced some heuristics on deciding the good alphas. Right? It is dependent on the upper bound, lower bound, the magnitude of the subgradient, and so on and so forth. Right? It is a quite complicated gradient, but you still need to do some parameter tuning, right? Especially for MILP problem. Once you have implemented it, you will recognize that. Now, the other tricky thing, if you still remember that, is it is not so straightforward to get a primal feasible solution. Right? So after you dualize the complicating constraint and solve the subproblem, right? The solution you got from the subproblems may not satisfy the complicating constraints, right? So because you see here, you already bring AX minus B to the objective, right? So when you solve for all the xi's, AX minus B has already been dualized, right? There's no guarantee the x you find, even if at the end of the algorithm, the xi's may not satisfy AX equals to B. Okay, this is especially relevant for MILP problem, right? Because for MILP, you don't even have strong duality. Then you need to design a heuristic to get a feasible solution to your original problem, right? Remember, one of the heuristic we talked about in the previous lecture is you take the average over all the subproblems, and then you do some rounding, right? Even if you have strong duality, you may find out that the primal constraint may not satisfy, right? Even if you have the optimal dual, then it could be the case that the problem is degenerate. You may not hit a solution that happens to satisfy the primal feasibility constraints. Okay, so that's the two issues you will face with dual decomposition. Okay, let's see if there are any questions here. Okay. So now let's try to address this issue by introducing the so-called augmented Lagrangian methods. Okay, from the name you can guess how it looks like, right? You will have this Lagrangian term plus a so-called augmentation term. So how do you interpret this augmentation term here? It is a square of the two norm ax minus b. Yeah.
It's sort of like just your squared error off of that constraint.
Yeah, right, yeah. So exactly. So if ax less than or equal to b is not zero here, you may not always have a positive penalty, right? Depending on what the optimal dual is. Here, if you square ax minus b, and rho is a constant greater than 0, as long as ax minus b is non-zero, you have a positive penalty, right? Yeah.
What's the point of dividing rho by 2 if it's just any random number?
Oh yeah, it's just by convention, because if you take the derivative, then the 2 disappear, right? So that's why usually people divide it by 2. Yeah. Okay. Any other questions? Okay. Yeah. So here you can view rho as a penalty parameter, right? Another way of viewing augmented Lagrangian is applying Lagrangian decomposition or dual decomposition to the following augmented problem, right? So this problem is clearly equivalent to the original problem, right? Because any x satisfying ax equals to b will get a 0 penalty here, right? So this is like adding a redundant term to the objective, right? Any feasible solution will get 0 penalty. Right, so you can view it as applying the Lagrangian to the same problem, right, with some sort of trivial reformulation. Okay. Now with that, we can use the dual decomposition and apply to this problem, right? And I mean, this problem is still convex, right? If you add a quadratic term with ax less than or equal to b, this penalty term is still a convex continuous function, right? That does not destroy the property of the original problem. Yeah, so now with that, we can have this algorithm called method of multiplier. Okay. Again, the idea is just to apply Lagrangian methods or dual ascent methods to the augmented problem, where you have an iteration where you first minimize over x, but over this augmented Lagrangian function instead of the Lagrangian function, right, with this quadratic penalty. And then you update y, still using this gradient step, right? It's the same step in terms of updating the dual. Okay, so this is known as the method of multiplier. Okay. Now the question is, how do we choose the step size? here, right, alpha k? Or is the step size alpha k related to the row here, right? Because the row is a penalty you picked, right? You can pick any arbitrary penalty row, right? So after we pick this parameter row, a natural question to ask is, what would be a good alpha to choose, right? So it appears that the good alpha to choose is to set alpha equals to rho. Okay, so if you look at some of the augmented Lagrangian method, they will tell you just set alpha equals to rho, right? So why is that? It may require some discussion, right? So here we will show you a motivation of why we should choose alpha equal to rho here, okay? So this is a justification in a few lines of very simple proof, right? Now, this is motivated by the optimality condition of the original problem, right? So if you write down the optimality condition, right, it is a convex objective with linear equality constraint, right? Therefore, the optimality condition is a KKT condition, right? So here we have primal feasibility and stationarity constraint, right? Because we don't have inequality constraint, there won't be any dual feasibility or complementarity. Right? The y is unconstrained. So we have these two conditions that gives you the optimality condition of the original problem. Now, one interesting observation here is if you, at this step, you are trying to minimize over x, right? So this is a arc mean step of y, right? So since this L rho is a convex function, the optimal x is obtained at derivative equals to 0. Right? So the optimality condition is the derivative of L rho with respect to x is 0. Right? So this is the optimality condition for the optimal x, xk plus 1. So if you write down the optimality condition for the gradient, we have the gradient on f of x and the gradient for the augmented term. Right? So if you do the math, you realize that this is the optimality condition for the minimization over x step. Okay. Now, why should we set yk plus 1 to be this term? The reason is because if you set yk plus 1 equals to this term, the xk plus 1 and yk plus 1 happen to satisfy the stationarity condition. Okay, again, when you are minimizing over x, right? So the xk plus 1 minimize this augmented Lagrangian term, right? And then if xk plus 1 minimize this augmented Lagrangian term, the gradient is 0 at xk plus 1, right? So if you take the gradient, you realize xk plus 1 satisfy this condition here, right? It equals to 0. Now, the next step is you want to update y to yk to yk plus 1. Right? So now the idea is what will be the good yk plus 1, right? Again, the goal is we want to satisfy the optimality condition. Right? We want to satisfy stationarity condition and primal feasibility. Because we want to satisfy the stationarity condition, you can find out that if you set yk plus 1 equals to this term here, then xk plus 1 and yk plus 1 together will satisfy the stationarity condition. Right? So that's why if you choose this alpha k equals to the rho here, then the next yk plus 1 will satisfy the stationarity condition. Yeah.
So I understand why we're doing it that way, but isn't rho, that's any weight that we want to add?
Yeah. So choosing rho is another story, right? It's quite arbitrary as well, right? But if you choose both rho and alpha arbitrarily, then you have two parameters too, right? Here is like saying after you have already picked some rho, what will be the good alpha to pick, right? Alpha is sort of not dependent on rho.
And then, I don't know if you'll talk about how to choose rho.
Yeah.
Should it be something that's roughly on the, that makes your gradient on the same magnitude as the, or makes your penalty on the same magnitude as your objective function? Because otherwise, it'll just ignore it. So it's not
Yeah, that's a great point. Yeah, we will talk about that in the next slide. But you got a very good intuition. Yeah. Any other questions? All right. Now let's talk about the pseudocode of these methods, right? One of the practical consideration here is finding the exact minimizer at each step might be impractical. So for the first few iterations, you may consider some early termination. The other thing is how to choose rho, right? In practice, you would gradually increase rho. Because if you want to satisfy the primal constraint AX equals to B, you would want this penalty to be large such that you can guarantee strict feasibility, right? So imagine if your penalty is infinity, right? Then, of course, numerically you would not set rho to be plus infinity, but imagine it can be set to plus infinity, then your solution must satisfy AX equals to B, right? It will not try to violate AX equals to B. But again, as Nex said, if you set rho to be too large, you got numerical issues, right? You are just trying to satisfy feasibility and ignore the optimality itself. Right? So that's why what you would usually do is to gradually increase the number rho from some small value where you first try to balance optimality. Then as the algorithm close to convergence, you try to balance feasibility. Okay, yeah. So here is the step, right? You will start with some rho, and for the next iteration, you will choose rho k plus 1 to be between rho k and plus infinity. Right? So there are different types of heuristics you could use. You can make rho to have some sort of exponential growth or linear growth, and so forth. Yeah.
Isn't it the same or almost the same as an interior point like that, in the sense that we had a like log approximation of indicator function, and now we have like a quadratic function, which is
So that's a very good point, right? The connection with
like L there, and we see rho here too.
Right. So your intuition is very good. In interior point method, you have this log barrier function to try to make sure the constraint is satisfied, right? One key difference between interior point methods and this penalty method is that in interior point method, you always get strict feasibility, right? You cannot have a log function where this constraint is violated, right? That violates the domain of the log function. But here in augmented Lagrangian, you can violate the constraint. As you increase the rho, you will converge to the point where you do not violate the constraint. But you can think about both methods as some sort of penalty-based methods. Okay, yeah. All right, so these are some quick convergence properties. Of course, we are not going to prove convergence because I don't know how to prove that, to be honest. You can check some of the references if you are curious about that. So typically what you will experience is that as the methods proceeds, the primal residual converge to 0. And then the idea is that this penalty term helps the convergence with dual ascent, right? Dual ascent does not always guarantee primal feasibility. Okay, but one downside of this approach is that this penalty term will destroy the decomposable structure of the problem, right? So if you consider, let's say, remember if we have, this decomposable problem, right? Once you dualize this complicating constraint, the problem can be decomposable, right? However, if you add a quadratic term, the problem will no longer be decomposable, right? So you have the quadratic term multiply each other. There are some multiplication between the two different blocks, right? So therefore, that's a downside of this approach, where the problem is no longer decomposable. So that's why we need to introduce another method called alternating direction methods of a multiplier. Right? So the idea is you will use the augmented Lagrangian type of methods, but you still want to keep the problem decomposable. Okay. So that's what we will talk about next. Okay. So here's the structure of these methods, right? Let's assume we have 2 blocks of variable. Of course, if you have n blocks, the idea will be very similar. At the end of the day, I will show you a problem with n blocks. But for the sake of the argument, we have 2 blocks of variables, x and z, right? And then we have 1 complicating constraints. Okay. Now with that, if you do the augmented Lagrangian here, right? So you have the y transpose ax plus bz minus c, right? So if you only have this Lagrangian term, the problem is still decomposable, right? Because this term and this term are linearly separable. However, if you introduce this quadratic term, right, you will have some terms where x will be multiplied to z, right? If you have this quadratic term, you have some terms x multiplied to z, and then they are no longer linearly separable, right? You look confused, right? So if you have this quadratic term, this is essentially rho ax minus bz minus c transpose ax minus bz minus c, right? That's what the 2 norm mean, right? A vector transpose a vector is a 2 norm, right? So with that, of course, you have some terms related to x, right? But you will also have the minus bz times ax, right? So therefore, you have some z times the x term from this multiplication, right? They cannot cancel out, right? So therefore, you have some x and z terms that are not linearly separable. The problem is no longer decomposable. Okay. Now, because in standard augmented Lagrangian, you will minimize this augmented Lagrangian term with respect to the primal variable xz jointly, right? But you have some couple quadratic term between x and z, and the separability is destroyed. Okay. So how do we retain this separability, right? In ADMM, what they do is we minimize x and z separately and sequentially. Okay, so this is an iteration of the ADM methods, right? Remember, in augmented Lagrangian, what we will do is first we minimize x and z jointly, right? So this is the argmin xz augmented Lagrangian xz yk, right? So this is what you will do in augmented Lagrangian, right? You are jointly minimizing x and z while fixing y to be the yk in your previous iteration. Okay, that's what you will do in augmented Lagrangian. since x and z we want x and z to be separable, what you can do in ADMM is, instead of optimizing x and z jointly, you will first optimize x, right? But if you just optimize x, you need to fix z and y at some value, right? So in this case, you just fix z at the value from its previous iteration, zk, and y from the previous iteration, right? And this problem is just optimizing over x. And once you have updated x to be the xk plus 1, then when you're optimizing z, you will fix x to be the value you just got, right, to xk plus 1. And y, since we haven't updated y yet, we just fix y still at the previous iteration. After you have updated xk and zk to xk plus 1 and zk plus 1, then you do the same dual ascent step to update the dual variable, right? Okay. Yeah.
So the point of separating it beforehand was so you could do it in parallel.
Mm-hmm.
This doesn't allow you to do it in parallel. You still have to go sequential. So how does this have any speed ups compared to just the normal method of multipliers?
Yeah, at least the problem size will be smaller, right? If you break down a problem to two different problems, the problem size will be smaller. The other thing is, I believe there are some extensions to the vanilla ADMM that will allow you to do it in parallel. Okay. One of the ways you can think about it is instead of using xk plus 1, you still use xk here. Right, so that's one of the, but it will affect the convergence in some ways. I don't know the convergence proof that well to tell you how will that affect the convergence. I would assume doing it sequentially will help the convergence, at least computationally. But then if you do it in parallel, you might want to fix the variable to the previous iteration rather than you have a new update. Okay. Yeah.
And that would be the same for yk plus 1 as you use the previous x and z, so then your yk would be a step behind everything else.
Yeah, so there are also some methods where the idea is they have an asynchronous update. Okay, but these are some of the latest literature developed in I would say in the last 5-10 years, right? In this parallel methods, what happens very often is, let's say you have hundreds of blocks, right? You need to solve in parallel. Not all the hundreds of blocks will terminate exactly on the same time, right? There probably will be a few blocks that slow down everything, right? So if you wait for all the hundreds of blocks, hundreds of processes to stop before you update the dual variable, you are always going to wait for the slowest process, right? So the idea of doing an asynchronous update in dual decomposition is that before I let all the processes terminate, I already update the dual variable and then throw in a new problem for all the process. Then you don't need to keep all your processes idle for a very long time, right? These are some recent research we won't discuss in class. You are curious, you can read the papers. Okay. Yeah. Okay, any other questions here? Yeah.
Maybe what's the point of doing all that? I mean, in the beginning, the interior point method, as far as I remember, we assumed that we deal with all equality constraints just by solving like one null space and taking one point, right?
Yeah.
And so what's the advantage? Is it like the fact that we can parallelize it, or is there?
Yeah, it's the advantage you can parallelize that. Yeah. 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 So. Yeah. Yeah. Yeah.
Isn't there a chance that it might lead to some sort of cycles because we are optimizing like one set of variables at a time?
Well, that is a matter of convergence proof, right? So how do you show that these type of methods can converge? I don't know the proof that well to answer that, but actually there are theoretical properties. I think if the problem is convex, you can show these type of methods can converge, right? Yeah. Okay. So yeah, so if you can check these methods, then there are a few main features, right? First, it does one cycle of block coordinate descent. Oh yeah, so we didn't talk about block coordinate descent. The idea of block coordinate descent is the following. If you have many variables in your optimization problem, right? So let's say we are talking about unconstrained convex problem, right? So if you want to minimize fx1, x2, all the way to xn, right? Now, in gradient descent, what you have is just take the gradient direction to minimize the value of fx, right? For some of the problems, taking the foot gradient is too expensive, right? The idea of a block coordinate descent is instead of taking the foot gradient, you take gradient of each block of variable separately. Right? So let's say x1 is the first variable here. We will just take the gradient with respect to x1, right? Or a partial derivative with respect to x1. Right? And then we will optimize the problem as this: f of x minus alpha times partial f partial x1. And then you can think about you write a vector as 1, 0, 0, 0, 0, right? So in the first iteration, you just update the first coordinate of the problem, right? And then you optimize the second coordinate and so forth. This is called a coordinate descent, right? Because you are minimizing each coordinate separately, right? And you can view ADMM as a so-called block coordinate descent, right? So x is a block of variable, z is a second block of variables. And then you first take the gradient term with respect to x, and then take the gradient with respect to z. Right? So if you have n blocks, you will do n iterations of descent, right? The advantage of block coordinate descent is that implementation-wise it's faster, right? For some problem, taking the gradient can be too expensive. Yeah. The other thing is that you can add some explicit constraint to x and z separately as long as they are decomposable. There are many applications of ADMM, especially in machine learning. If you are into machine learning, there are many applications like federated learning. The idea is instead of training one neural network on a single machine, you have different sub-processes, right? Each of the sub-processes has their own data to update the model. And then you can coordinate them using ADMM type of methods. Yeah. And then if you have some distributed computation hardware, then you could solve a problem using distributed optimization. All right, now let's talk a bit about optimality conditions in ADMM, right? So you could think about how do we choose the update parameters alpha, right? So, by the same argument, you will choose these update parameters alpha, the same thing as what we did before, right? Just set alpha equals to rho. That is because of the optimality condition we discussed before. You want to satisfy the stationarity conditions, right? That's why alpha has to be set equals to rho. I won't talk about that again. So this is a quick summary of the convergence results for ADMM, right? Again, I don't know how to prove that. If you are interested, you can read some of the references we gave you. Under two assumptions, first is we have extended real value functions are closed, proper, and convex, right? So most of these properties are standard property, right? Especially if you have convex functions. And then the unaugmented Lagrangian has a saddle point. Okay, so with that you can show the convergence, right? When you talk about convergence of ADMM, I would say there are two major things. One is the residual, the primal constraint converges to zero. That gives you the primal feasibility. Then the objective converge to the optimal primal objective, and then the dual variable converge to the dual variable, the optimal dual. Right? And that's what people have shown before. Right? So these two assumptions are very weak assumptions, I would say, right? They are not that strong. As long as you satisfy convexity, then for most of the, let's say, good-looking problems, if it's convex, you can show ADMM has convergence. Yeah, so here's a quick extension of ADMM to what is called consensus optimization problem, or you can think about this as an analogy with non-anticipativity constraint. Right? You have n problems. You want to create some copies of these n problems, but then you have to create some non-anticipativity constraint to make sure that all the x you created for each subproblem are the same. So here's what the type of problem you have. You have a minimizing over fi of x, right? So all the fi's are using all the x variables. But in order to make all the fi of x separable, then you can create a copy for each of these problems, f from 1 to n. But at the end of the day, you need to make sure all the copies you created are the same. Right? So you can define a so-called global variable z and set it equal to all the I from 1 to n you've created, right? Or you could also treat x1 as a global variable and set all the others equals to x1, right? But here, for notation convenience, we just assume we have defined a so-called global variable z, right? And you set all the local variable equals to z. So this is called consistency or consensus constraints or global consensus problem. But if you want to make an analogy, this is like the non-anticipativity constraint we talked before, like in stochastic programming. Yeah, so how do you apply ADMM to this problem? You can naively apply ADMM to this problem, and it has n blocks, right? So the dual variable for the constraints for the ith problem is yi, right? And then you dualize these consensus constraints and penalize the consensus constraints, right? They are in total n sets of consensus constraints. So with that, you could update each of these xi separately, right? So in this case, we are not strictly following the ADMM, right? Because you want to update all the xi's individually instead of sequentially, right? So in this case, you are keeping all the other xi's as okay. So you probably don't need that here because this is already sort of a separable problem here. Okay, so you can update each of the blocks xi separately, and then at the end of the day, you could update the z variables, then update the dual variables. Right? So this is an application of ADMM to a problem with n separate blocks. There are a few other methods related to ADMM in the literature. They are called things like operator splitting methods, proximal point methods. There are also things called progressive hedging methods. When you have seen this, they look very similar to ADMM. Okay. Yeah, so I want to give a few comments on the application of ADMM to mixed integer linear programming problem, right? So as you can see from the dates of those papers, most of these papers are quite recent. Right? The thing is that all these convergence properties we covered in the lecture, they only apply for convex problem, right? So convergence of ADMM for non-convex problem were recently studied, but there are some good results, but it's still an ongoing research. If you are curious about that, you can check some of these papers I listed. All right, so here's the references, right? Most of the people will refer to this tutorial by Stephen Boyd and co-authors on ADMM, right? And then they apply this type of problem to some statistical learning problems. You can also check the numerical optimization textbook. I think Stephen Boyd also has some slides you can refer to. Okay, so yeah, that's all.